Okay, so the aldol condensation makes alpha beta unsaturated ketones, and one of the reasons that it's so important is because the products are also highly functionalized compounds that can do a lot of things. And one of the things that's quite unusual is that these hydrogens here at the beta carbon, if we have hydrogens there, so an alkyl group, in this case a methyl group, are as acidic as the alpha hydrogens next to the carbonyl up here. So we get additional chemistry that is possible out of an enone like that. Not surprising, okay? Because an enone is nothing else than an oxygen analog of butadiene. And butadiene, remember, conjugated, the two ends communicate, they know of each other. So this oxygen knows that there's this carbon here. In fact, you can almost think of this as this cutting out these two carbons as if this oxygen were sitting directly here on this carbon. Because by resonance, you can put a positive charge on this carbon. Or putting it differently, if you write the dipolar resonance form of the carbonyl, O minus, C plus, then this positively charged carbon is in resonance, in allylic carbocation resonance with this carbon over here. Okay? And that means that the electron withdrawing power of this oxygen goes all the way down the line. And if you had several double bonds, it will communicate all the way to the end. If there's 1,000 of them, in principle, the last carbon at the end will know that there's a carbonyl at the other end pulling on it. And that's the beauty of conjugated systems. They are like metals, like wires. Okay? They communicate the electronic environment down the line. Okay? So how do we make these compounds? Well, aldol is one way, but we already know actually how to make them by traditional ways. One is you can halogenate a carbonyl compound, we learned that last week, by acid-catalyzed bromination or chlorination. Remember that goes singly, it introduces only one halogen, and you get an alpha or 2-chloro or 2-bromo carbonyl compound. Haloalkanes can be eliminated with base, so you just treat those with base and you get an E2 elimination. That puts in the double bond. That's traditional E2 stuff. We also learned that allylic alcohols can be oxidized with manganese dioxide. Here's an example. That also makes alpha beta unsaturated carbonyls. Okay? We made those before. We didn't mention anything special about them, but that's in this context of this chapter. That's one other synthesis of these guys. Then we have the aldol condensation. And then the fourth one is an old one. It's the Wittig reaction. And it's a Wittig reaction where we use stabilized ylids. We did this briefly last week. Stabilized ylids are typically those that have additional double bonds, often carbonyls. So if you take chloroacetaldehyde, which you can make by chlorinating acetaldehyde with acid, and with triphenylphosphine, you get this phosphonium salt. And this phosphonium salt has now an extraordinarily acidic hydrogen here. It's more acidic than water, so you can pull it up with sodium hydroxide quantitatively, because not only does it have the positive charge of the phosphorus next door, but it's got a carbonyl next door. Okay? So it can form a resonance form as an enolate. So after deprotonation, you get this beast here. Here I've written the valence shell expanded ylid structure. You can write the octet structure if you want. But from here, you realize this is nothing else but an enolate anion, so we can have the negative charge here. And writing out these resonance forms explains something that some of you may have been puzzled about last week when we did the BASF vitamin A synthesis using an ylid oh no, this was not an ylid with a carbonyl, so this actually example is no good. So you can do Wittig reactions with this ylid here, and you may wonder, how is this possible? How can you do a Wittig reaction with a reagent that has a carbonyl built into it, right? That looks like an automatic loser, okay? And the reason is because of these resonance pictures, this carbonyl is not really a carbonyl, it's an enolate. And so that resonance form protects the carbonyl from the usual ylid type reactivity, which is the carb anion attacking the carbonyl. Okay? And so these guys can be isolated and then reacted with aldehydes. In fact, as it turns out, stabilized ylids, this is something we didn't specifically mention last week, only react with aldehydes. They are sufficiently stable that they only do the Wittig reaction with the more reactive aldehydes. Ketones are no good for this. So if you react this ylid with the aldehyde, out comes the alpha beta unsaturated carbonyl. And you may remember stabilized ylids preferentially give trans products. Non-stabilized ylids give cis in the Wittig reaction. Okay? So here's the trans compound. So 4 ways of making alpha beta unsaturated carbonyls. So why are they important? Well, they're stabilized by resonance. So the resonance picture can be shown nicely with these resonance forms. So you have the neutral one, and then you can take the electron pair out, make the O minus, and here's the carbocation structure. And this one, as drawn, clearly is an allylic carbocation, so you can do the allylic transposition, 1,3, the charge jumps 1,3, and that puts a positive charge on this carbon. And that is very important because that means that that carbon is electrophilic. That carbon is transposed, so it's from here to here. That carbon is also electrophilic. Both of them are electrophilic. It's nothing else but a glorified allylic carbocation, where the two ends are different, but they're both electrophilic. And that can be shown in an electrostatic potential map. Here's the carbonyl function. Here's this carbon. A lot of blue, of course, because that's the carbonyl carbon. But there's a fair amount of blue, well, sort of greenish blue, on this carbon over here, indicating that there is carbocation character at this carbon. Notice that this entire region here, which is a double bond, and normally in the electrostatic potential maps, double bonds are red, is already off completely, more in the direction of blue, so green-blue, because of the electron withdrawing power of the carbonyl function. So, as a consequence of resonance, it means that double bonds next to a carbonyl are more stable than isomers in which the double bond is removed from the neighboring position of the carbonyl. And when this transposition is only one carbon away, because, as in, for example, this beta-gamma unsaturated aldehyde, 3-butanol, because this guy is enolizable, you can rearrange this from here into the isomer that is more stable, but simply by adding acid or base. Okay? So it's a tautomerism that leads from the non-conjugated enol to the conjugated enol. So acid or base catalyzed is very simple. It goes through enol formation or enolate formation. With acid, you form the enol, and the enol then has the double bond already in conjugation, and then you reprotonate at this carbon here to make this guy. With base, you deprotonate first to make the enolate. And the enolate is an allylic anion that's delocalized, and then you reprotonate at this carbon. Here it is. Acid, you just do the acid-catalyzed keto-enol tautomerization. Ignore this double bond for a moment. Protonate here, and then deprotonate here. That makes the enol. At this stage, these guys are already in conjugation. Okay. This is unstable. This is a dienol. It's as unstable as the normal enol, but reprotonation occurs here, because it forms this carbocation, which is nothing else but the protonated product. Okay? So this is all we're doing the same chemistry, but we're interspersing an extra double bond. But everything else is the same. And out comes the more stable alpha beta unsaturated carbonyl. Base catalyzed, we're changing the sequence. Acid catalyzed, we protonate first, deprotonate later. Base catalyzed, we deprotonate first, and then protonate later. So now we're deprotonating this to make the enolate. The enolate has 3 resonance forms. We just did this. And one of them is the negative charge being on the terminus. You reprotonate here. Out comes the more stable product. Again, I'm just drawing the mechanisms that lead to product. All other reprotonations or deprotonations which may be occurring are dead-end streets. They lead to less stable products. Everything's reversible, so the equilibrium eventually shifts to the more stable component. So what's the reactivity? There is one part of enons that is conventional reactivity. That is, you treat the 2 functions, a CC double bond and the carbonyl, as separate entities, and they react the way that we are used to, namely the CC double bond undergoes additions in its own way, and the carbonyl bond undergoes addition in their own way. And this is sort of generalized here. CC double bond may add reagents AB. The carbonyl may add reagents AB. For example, catalytic hydrogenation. The double bond is more reactive than the carbonyl. Remember, the CO double bond is stronger than the CC double bond because there's a strong polar component to the CO double bond, makes it a stronger bond than the CC double bond. And so ordinary palladium on carbon hydrogenation selectively hydrogenates this double bond. In fact, typically the carbonyl function is stable under catalytic hydrogenation conditions. You can hydrogenate carbonyl functions. It's done in industry. You need high pressure, special catalyst, sometimes elevated temperatures depending on the system. So they're hard to hydrogenate. So in an enon, selectively only the CC double bond. Alkyl lithiums and Grignard reagents add to the carbonyl function to make the normal addition products. Okay? As we are talking about this, as an aside, you may have wondered, alkyl lithium and Grignard reagents, they are not only nucleophilic, they're also strong bases. Why do they attack the carbonyl group? Why don't they deprotonate, like LDA? And the answer is, they sometimes, to some extent, but typically, they go Coulomb's law for the positively charged on the carbonyl carbon faster, okay? So that they don't act typically as bases. And you get, in just ordinary carbonyl additions, you don't get deprotonation. So if you want the enolate, you use LDA. Okay? Just on the side here. So normal chemistry to the carbonyl. And then you also get the bromination, for example. That's normal CC double bond additions. You get the dibromine. So that's all normal. Okay? It gets interesting when we look at the enon function as a conjugated system where the 2 ends communicate. And that becomes significant when we do reversible ionic type additions of the type that we've been discussing the last 2 weeks, like HCN, water, alcohols, amines. Okay? Because then this resonance structure here, which has a plus charge on this carbon, and the enolate structure here becomes significant, meaning this carbon becomes nucleophilic, or can act as the nucleophilic component. So that AB reagents, where A typically is a proton, such as in, let's say, HCN, lead to additions where the cyanide, or the B component, adds to the electrophilic beta carbon of the carbonyl function, and the proton, as usual, winds up on the oxygen, and of course that is an enol, and so the enol tautomerizes to the carbonyl. So that you have additions where, rather than B, the nucleophile, adding to the carbonyl carbon, it actually adds to the beta carbon and winds up as such in the product. That seems incomprehensible, maybe. Well, plausible, but your question, which is rightly taken, we just learned the last 2 weeks that nucleophiles attack the carbonyl carbon. That's why we get carbonyls as hydrates and hemiacetals and then acetals and hemiaminals and cyanide made hydroxycyanides. So why should it now attack here, especially since we learned that there is actually a little less blue here than there is here? So that carbonyl carbon should be more reactive. And the answer is, it does. Addition to the carbonyl carbon is actually faster, and it will add. But now, again, it's reversible, and since we have an enon with another nucleophilic carbon, there's another option as it goes back and forth. And that option actually leads to the thermodynamically more stable product. Because in that option, where you add B and then ultimately H across the CC double bond, you're killing a CC double bond. In the other option, adding across here, you're killing a CO double bond. And the CO double bond is stronger than the CC double bond. So thermodynamically, when there is the option of adding here, you actually lead to a more stable product, addition product. So that's almost diabolical, right? You're giving the molecule, you learn all this carbonyl chemistry, you add a double bond, and now suddenly it changes. And the reason is purely everything is reversible. It finds a way to a more stable compound. So let me give you a specific example, starting with hydrogen cyanide. And these additions, by the way, are so-called conjugate additions because they take into account the fact that the enon is a conjugated system. If you treat this with acidic KCN, which is nothing else but glorified HCN, under acidic conditions, you protonate here, it activates the system, and cyanide now adds to this carbon here to give you this beast here. And this is a very useful transformation because, again, we're making a new carbon-carbon bond, but now the beta carbon, and as I mentioned before, nitriles are very useful functional groups of the CN triple bond that can be converted into all kinds of carboxylic acid derivatives, which we'll learn about in the next chapters. So we're not getting addition of HCN across the carbonyl as the product. But in fact, that addition is faster than the one that leads to the final product. So cyanide still more rapidly adds to the carbonyl carbon to make the hydroxycyanide there. But it's reversible, and it now realizes it has another option, namely adding to this carbon, and that leads to, in this equilibrium, to the more stable compound. So what's the mechanism? It's now pretty straightforward. It's the vanillagous analog of the HCN addition to the carbonyl. So we activate by protonation, as we usually do, and that activates the carbonyl. But by relay, because it's conjugated, it also activates the beta carbon. And you can see this clearly through this resonance form. It's an allylic carbocation, and so we have a carbocation resonance form shown here. Then from this form, cyanide attacks at this carbon. So I'm just for the fun of it, I'm using this resonance form. Remember, these three pictures are the same molecule. They're not isomers. The true structure of the molecule is superimposing all three on top of each other. So you can use any one of the three to do the cyanide addition. So I'm picking this one because then I can push three arrows. Okay? So I can attack here, this electron pair goes here, this electron pair goes out, and that gives you the addition product initially as the enol, and then the enol undergoes enol keto tautomerization to the final product. So this works not only with HCN, but as we shall see on Thursday, with water, with alcohol, and with amines. They're all additions to the beta carbon, even with enolates, as we shall see. So everything we've learned so far on adding to the carbonyl function itself also happens to alpha, beta, unsaturated ketones. See you on Thursday. Thank you.